Good afternoon, ladies and gentlemen. I would like to thank the ASCE for holding the Innovation Contest and having this award presentation. I'm very pleased to be here today to present details behind the design and operation of the Rainmaker water harvesting system. As you can see, our goal is to harvest water from unconventional sources. I will detail these sources and the applications where the Rainmaker will create potable water. Now, if you are like me, you come across times in your life where an off-the-cuff comment gives you an aha moment. One such moment came to me about 4 years ago when I was on LinkedIn's Geological Society of America group. You see, I'm a graduate geologist from back in the day when there were no environmental engineers. An industry was scrambling to find people from related disciplines to mold into the first environmental engineers so that they could comply with the recently enacted Clean Water Act. As such, I like to keep my geology roots current and keep track of what is going on in the geology world. It was here I came across an interesting question from an electrical engineer from Saudi Arabia. Could a mountain be constructed high enough in Saudi Arabia to allow glacier formation so that permanent rivers could be produced? Well, this question piqued my interest, so I spent the next 10 minutes checking the NOAA website to see if there was enough water vapor available in the atmosphere above Saudi Arabia to allow precipitation at high elevations. My quick review indicated that there was not sufficient water vapor to support glacial formation. I wrote a quick reply to the engineer stating that I did not believe glaciers could be formed on a mountain in Saudi Arabia, but I did say that perhaps a technological means could produce the same effect. Afterwards, my thoughts turned to the water cycle. It's pretty straightforward. Water is evaporated and eventually condenses in the form of rain or snow to return to the earth. Now, in most treatment processes, we look to mimic nature, which itself does provide treatment, provided enough time is given in the local environment and it is not totally overloaded by contaminants. Now, as with any treatment process, our goal is to reduce the amount of time required to effect this treatment. But before we get into the details of the water harvester, let's take a look at the acknowledged water problem that currently exists and is anticipated to only worsen as the years go by. According to the World Health Organization, there are over 1.8 billion people without daily access to safe water in the world, and over 1 billion of these people do not even have access to sufficient water. The main causes for this lack of safe water are drought and overpopulation. To emphasize the water problems, here's a graph showing the effects of water shortages in 2004. You notice the darker reddish area, the oranges and reds, where there are water stress noted. They are concentrated in the west and midwest of the United States, the Pacific coast of South America, South Africa, the Mediterranean basin, and from the Middle East stretching into India and China. Now jumping forward to 2040, we see that much greater portions of the world in red. This is where significant water stress will be seen far beyond that seen in 2004 or even today. With many of the current water sources overstressed to meet the demands to supply sufficient water to the world's population, new sources must be found, and there is readily available water to be found from unconventional sources. These sources include seawater, hypersaline waters, where salt concentrations are over 50,000 milligrams per liter. These would include the fracking water, oil gas product water, and natural bodies such as the Dead Sea or Great Salt Lake. Brackish waters, where salt concentration is in excess of 1,000 milligrams per liter. We see this in bays and estuaries. Then add to that any saline aquifer that may be out there. Also flows being discharged from mining operations, along with the possibility to recycle wastewater or treat polluted freshwater sources. With the development of the Rainmaker's new evaporative water harvesting methods, all these unconventional sources can be used to obtain potable water. Our development status is that we have completed our lab scale testing and planning for the next stage where we will begin to field test a prototype for either acid mine treatment or product water from the Marcellus gas play. The prototype stage will move us forward as funding is obtained. The concept behind the Rainmaker water harvester is quite simple. Mimic the natural water cycle. Heat the air, then move the air over the water. The water is evaporated into the air, and finally introduce it into a condensation chamber, making it rain. We're just speeding up Mother Nature. Here is the formula for velocity-induced evaporation. It is really just a function of the surface area of the water, the speed of the air traversing it, and the humidity already present in the air. With the next series of slides, I'd like to go over the process flow diagrams for the various applications where we will be looking to operate the Rainmaker. In this slide, we look at the process flow diagram for desalination water harvesting, where we remove salts from the process water. As shown, we are looking at desalinating seawater, average salt concentration of about 35,000 milligrams per liter. As we noted before, the process is relatively simple. Bring the seawater into the system, screen out any large particles, and pass the flow through the heat exchanger, which is used as a heat sink for the chiller system. The water then passes into the evaporation chamber. The next component we look at is the air handling system. This is a closed-loop system that is the reactive medium and carries the evaporated water through the system. But first it must be heated, which requires a liquid-to-air heat exchanger. Liquid is heated in a thermal heliostat that utilizes a disc-shaped solar concentrator, which constantly circulates from the heliostat to the heat exchanger and back. The heliostat gives us 1 million BTUs, that's British thermal units, even in Pennsylvania, allowing efficient operation where our operating temperature for the air will be in excess of 80 degrees centigrade. We do this to increase the liquid carrying capabilities of the air. The air is then passed over the quiescent water surface in a specially designed evaporation basin. The contact zone of these basins vary in size, depending on the module that is being produced for an application. The near saturated air leaves the evaporation basin and continues on into the microclimate condensation chamber of the Rainmaker, where it precipitates. Since the Rainmaker minimizes the amount of energy required for desalination, we can look at providing electrical power for the system through either photovoltaic or wind turbines while incorporating a battery system to allow for 24-hour operation. A major problem with desalination systems is what to do with the reject brine. Our design is to reduce the amount of brine produced to 10% of the input. For example, a 20 million gallon per day plant will require a bit over 22 million gallons per day of seawater intake. 2 million gallons may sound like a lot, but it is a significant reduction from the 20 million gallon reject from a similarly sized reverse osmosis plant. This remaining brine should not be looked at as a waste product, since the Rainmaker is an evaporative system, and we continue to concentrate the dissolved solids with each pass through the system. We will discuss the resource recovery circuit shown on the seawater desal slide later in the presentation. Now, seawater is not the only saline water that can be treated by this water harvesting system. Because of the evaporative nature of the system, hypersaline waters such as frac water or product water from the oil and gas operations can also be treated by this version of the system. Salt concentrations here will range from 180,000 to 300,000 milligrams per liter. Our next application is very similar. It is for the treatment of AMD, abandoned mine waters. But there are adjustments that have to be considered, as the majority of the metal salts present in the AMD flows can produce some very nasty precipitates. You see, the basic PFD is the same as the seawater in the hypersaline waters, but it also requires an addition of a pH adjustment cycle to ensure that the hydroxide precipitates are not produced during the treatment process. I previously spoke about the resource recovery, and specifically what I'm talking about is the ability to recover metals that are in solution in seawater, fracking product waters, and in AMD. This will require a separate circuit, smaller than the original process circuit, but it will function approximately the same and will keep producing additional potable water as we continue to concentrate the metals. Of most interest for this system is recovery of dissolved metals like uranium, lithium, and the rare earth metals. Other metals present in the varying concentrations that can be readily removed include the precious metal groups gold, silver, platinum, then iron, manganese, aluminum, lead, copper, and zinc. The resource recovery circuit will take the brine concentrate and put it through the circuit numerous times. We can expect an 80 to 90% increase in concentration with each pass through the device. Our goal is to increase the concentration from the microgram per liter range to the 1 to 2% range where conventional metal processing circuits can utilize the concentrate as feedstock. Or as an alternative, we have been in discussions with the Oak Ridge National Laboratory to investigate the use of their patented high-cap process for selective metal ion removal. The high-cap process is rate-limited with respect to the concentration, so the higher the concentration, the faster the rate of deposition onto the substrate. It sounds like a perfect match for the Rainmaker. We expect the advantage of the resource recovery circuit will lead to its inclusion for metals removal at many desalination facilities. When we initially looked at municipal wastewater, we felt the Rainmaker could easily be added as a tertiary treatment stage for purple pipe recycling applications. Then we started thinking more deeply about the various wastewater treatment processes and how to apply the water harvester to them. With respect to secondary treatment, there should be similar results by the unit when taking primary effluent and using the system as a combination secondary-tertiary treatment system. As you can see from the process flow diagram, the majority of the components are the same as with desalination. But when you take a close look, you see there's another circuit that we can discuss in our next slide, where feedstock for anaerobic reactors can be created by the water harvester. Our wastewater to energy WW2E process, which we feel is theoretically viable, has in and of itself the potential to be a paradigm-shifting development for the treatment of municipal wastewater. With this process, we have the potential to eliminate aerobic secondary treatment of low-strength wastewater. The strength of wastewater is measured by the biochemical oxygen demand, or BOD for short. Since the water harvester is an evaporative system, we remove approximately 90% of the water on each pass through the system. Thus, the remaining BOD in the concentrate will increase approximately by an order of magnitude. For example, for a BOD with an incoming strength of 200 milligram per liter, it will be concentrated to 2,000 milligram per liter after a single pass through the water harvester. We now exceed the minimum 1,000 milligrams per liter BOD required for an anaerobic reactor feedstock. Accomplishing all secondary treatment through anaerobic processes will eliminate tremendous amounts of energy now used for aerator blowers while creating sustainable wastewater treatment operation, as we can now use the biogases generated by the anaerobic treatment process to operate the wastewater plants. Once our pilot plant being utilized for the desalination trials is available, we anticipate pilot testing this very intriguing process in central Pennsylvania in mid-2019. Now, the advantage with the water harvesting technology developed by Twin Oaks is that the process is designed from the start to be scalable. Units are designed for flows ranging from 5,000 to 100,000 gallons per day that are trailer mounted, and for fixed operation using 5, 10, and 20 million gallon per day modules. These sizes have been selected with the idea of multiple units being placed in parallel operations, as in standard treatment plant design. This is a drawing of our Model ST treatment plant. It only utilizes solar energy to heat the air for the system and is rated for a maximum of 18,000 gallons per day. All necessary process treatment is mounted on a single 53-foot trailer. These units are anticipated to be used in desert coastal climates. On this slide, we show the operating curve for the ST1 module, where on a single pass, approximately 60% of the water present in the air will be precipitated. With 2 additional condenser stages, the air will precipitate 90 to 95% of the water present. Now, for operation in areas where the solar gain is less, or for a 24-hour operation, the mobile Model OG Rainmaker is used. It has a larger capacity and can operate 24 hours per day, utilizing gas-powered or thermal heliostat heating combined with thermal storage. It's a dual trailer unit with evaporator, air heating chamber on one trailer, and the condenser unit and ancillary equipment, such as the gas-fired heater or heat exchangers, on a second trailer. The chiller is located next to the heat sink that accepts the incoming flow. This unit is specifically designed for treating fracking or product water derived from the oil and gas operations, so solids are screened prior to entering the unit as part of another operation. However, this unit can be used for other applications, but pre-screening will be required. As you can see from the operation curve, the Model OG will obtain approximately 100,000 gallons per day. For this unit, to obtain 100,000 gallons, we pump approximately 200,000 gallons a day through the unit, although the actual input to the system will be approximately 110,000 gallons, leaving 10,000 gallons of reject brine to be handled by secondary systems. In this slide, we show a fixed Model ST module that is capable of producing 5 million gallons per day. It is strictly a solar unit for high solar gain areas. The air heating and evaporation basin is approximately 60 by 80 meters. The fan buildings are located on the right-hand side of the evaporation tank, while the Rainmaker condenser units are located on the left-hand side. These units will be oriented in an east to west layout to take advantage of presenting the greatest surface area to the sun for thermal uptake. These units are rated at a nominal 5 million gallons a day. The curve shows that the instantaneous rates will vary from over 6 to close to 15 million gallons a day based on the amount of solar energy absorbed into the system. As with the mobile ST unit, it is assumed that this unit will be operating at maximum efficiency during the daylight hours and at a lesser efficiency as the air cools overnight. The next size module that we're looking at is a 20 million gallon per day solar power module. The difference here is we will be using thermal heliostats to heat the air. As you see from the profile, there is considerably less superstructure over the evaporation basin as compared to the solar unit. The evaporation basin, though, is the same dimensions as with the 5 MGD unit, 60 by 80 meters. The condenser section is similarly sized to the 5 MGD module. But in this version, you'll see an additional building structure where the main air heating occurs as the heat from the thermal heliostats is exchanged into the process air. Here's the operational curve for the 20 MGD module. The air temperature during normal 24-hour operation will be at 95 degrees centigrade by using multiple thermal heliostats. With the Rainmaker's new concept of water harvesting through evaporative means, we create distinct advantages over distillation and reverse osmosis methods to desalinate saline waters. These include lower capital costs, where we anticipate the cost of the equipment for the Rainmaker to be 35% less. The operating costs should range from 50 to 75%, but it is in the reduction of energy costs that the unit saves the most money. We will see 50 to 90% less energy required to obtain the same amount of water. Additionally, the footprint will see a 25 to 50% reduction in area required for the installation of the units. By reducing the energy needs of the process equipment, we will utilize sustainable energy sources such as solar thermal, photovoltaic, biogas, or wind energy to obtain equal amounts of water as currently produced by RO or distillation. We expect the Rainmaker to be the sustainable solution for water and wastewater treatment as we move forward. Thank you for taking the time to view this presentation. It was originally presented at the ASCE Innovation Contest award ceremonies in June 2017. Now, I'll be happy to entertain any questions that you may have. Our contact information is located here on the website. Thank you again.